Hi class, welcome to the next video, chapter 1.2. Today we're going to go over the library of functions. So in the last video we talked about functions quite a bit. We talked about transformations of functions. So in this section we're really just going to review the main parent functions. So this video is going to be really quick, probably like 5 minutes or something like that, which is nice. It's always nice to have a short section. So let's go ahead and get into it. So we're really just going to talk about the main general functions that we use in algebra and calculus and so forth. So our library of functions are as follows. Okay. First we have a line. The most basic line is just f of x equals x. So I know we're probably used to y equals mx plus b, but this is the most simple case, right? So if you think about y equals mx plus b, we have a horizontal compression or expansion of m, our slope, right? And we have a vertical translation up and down of b when we have y equals mx plus b, right? So even just the general form that we're used to is a transformation of the most basic line of just x, right? Slope of 1, the intercept is at the origin, basic function, okay? Our next most basic function is x squared, right? And again, you're probably used to the expanded form of a quadratic, right? ax squared plus bx plus c, which we can always sort of generalize into the translated form of, you know, the vertex form, okay? Where we have a times x minus h squared plus k would be the same thing as ax squared plus bx plus c, but then in a form where it's very easy to see what the up and down shifts are, the left and right, and how wide or thin we have to compress the parabola. So the basic function of that, the parent function of a quadratic, is x squared, okay? Similarly, we have x cubed, 1 over x, which we saw earlier. We have 1 over x squared, which is very similar to 1 over x, but everything remains positive because when you square something, you only have positives, right? And it also, in the case of 1 over x squared, it goes to 0 a little bit faster than 1 over x does, okay? Because the large values are on the denominator. So here, everything remains positive. Here we have 2 to the x, but this can be replaced with any kind of base, right? This could be 3 to the x, 1/2 x, e to the x, but all of those are different transformations of a standard exponential function, okay? But I just randomly chose the base 2 because it's very basic, okay? Could have chose e to the x as well. Then the next transformation, or sorry, the next parent function we have is the standard log function. And square root of x, which always remains positive, and of course we can move this left to right, up and down, make it grow slower or faster, things like that. Okay, so these are the other parent functions. We have one more, which is the absolute value of x. Okay, now there are other functions. For instance, you see here we have x squared, then x cubed. I could put x to the 4th, x to the 5th, x to the 6th, things like that. But that's not very useful for us. We'll talk about those things when we get into polynomials. Those are called power functions, right? Obviously, I have 1 over x and then 1 over x squared. I can have 1 over x cubed, 1 over x 4th, things like that. But we really just kind of need to see the first two to kind of see what's happening. Here you see we have actually the first 3 polynomials, x, x squared, x cubed, and so forth. So it actually has a pattern being developed right now with just these 3, which again we'll talk about more in the section for polynomials. And here we're starting to look at the pattern for what happens for 1 over some power of x, right? We have 1 over x, then 1 over x squared, and then we could talk about the next one and so forth, okay? 2 to the x and log of x, these are inverses of each other, which we'll cover later on in chapter 1 as well. Okay, square root of x is a very standard parent function as well. We talk about square roots quite a bit in this course, actually. And absolute value. We don't use this a whole bunch, but it is important to discuss. Okay, so it's really just a line, but always positive, so that's why it looks like a V, right? So when we talk about these things, obviously, you know, from the last section, we're interested in transforming these things, moving them left, right, up, and down, making them wider, thinner, larger, smaller, things like that, right? But really, when we're dealing with things in calculus, a lot of times we're dealing with things that are non-continuous. So an important application of these is the piecewise function. Okay, so that's really what we're going to kind of focus on in this section, is the piecewise portion of these, which is defining these functions, several of these functions, in one graph, but over different intervals of existence, different domains. Okay, so let's look at the following. So I have a linear function whose domain of existence is the following. Okay, from negative infinity to negative 4, including that value of negative 4. Then I have this linear function from negative 4 to 0, the boundaries not being included, right? So basically what I'm doing is I'm defining a function over a certain interval, okay? So my function is comprised of several functions where they exist in pieces, right? And the intervals in which they exist are given second, okay? So first it's what the actual function is, second is the interval of existence for this graph. Next we have x squared from 0 to 2, and 1/2 x minus to the x minus 4 power from 2 to infinity. So I have a linear function, I have a shifted linear function, a quadratic, right, a power function, and an exponential function. So it's easy, it's nice because I know that this is a base of 2 with the negative exponent, right, which gives me 1/2, right? Or we can think of this as the reciprocal of 2, which is the same thing. And I have a shift in my exponent. It's not just 1/2 to the x, but it's 1/2 to the x shifted by 4, right? And it's shifted to the right by 4 units because it's x minus 4. It's being applied directly to the x. Okay. So let's go ahead and graph this in pieces, right? So first we'll just graph the first part over this interval, then the next part over this interval, and so forth and so forth. So I have an output of 2 all the way until negative 4. Negative 4 is included in this graph, right? So I have an output of 2 all the way to negative 4. Negative 4 is included. Okay. My next will be 1/2 x plus 2 from negative 4 to 0. So for positive 1/2 x plus 2. So what I'm going to do is I'm going to figure out, I can either draw this whole graph, so I know it's I have a y-intercept of 2, and it's 1/2. Right, so that means up 1 over 2, up 1 over 2, up 1 over 2. I could draw that for the whole graph and then just erase the parts where it doesn't exist, okay? Or I can start here and know that I go down 1 over 2, down 1 over 2, and say, okay, this is where I'm gonna start, and then draw my graph only until where it exists, which is until 0, okay? So there's kind of two ways to do this. One is, again, just draw the whole line and erase the parts where it doesn't exist, or just kind of figure it out, like, hey, for this function I'm starting at negative 4, so what do I have? Well, if I plug in negative 4, I get negative 2 plus 2, so that's 0. When I plug in 0, I get out 2, so that means at negative 4 I'm at 0, and at 0 I'm at 2, right? So I can just evaluate on my bounds and know that I go, this is one point, and then this is the end point. Right? When I plug in negative 4, I get out 0. When I plug in 0, I get out 2. So I know it's a straight line. I can just connect those two lines. Or figure out one of your points and apply your slope, right? So we're not going to go over all of that stuff because, again, this is a calculus class, not an algebra class. But you should know how to, plot a line, the whole thing, and erase what's missing, or just the existence, okay? So I also know that I do not exist at these boundaries, right? They're open parentheses. So that means that for my line, I have an open endpoint for both, okay? Which means that if I try to evaluate my function at negative 4, this is not the value that I get out. This is the value I get out, okay? So if I plug in negative 4 to my function, this is the function it goes with, not this one. So it's an open circle here, closed circle here. The next function was x squared, I believe, from 0 to 2. Okay, so from 0, I get out a 0 in x squared. When I plug in 2 into x squared, I get out 4. So I'll have a half of a parabola, basically from 0 to 2 here. Okay, I exist at the boundaries 0 to 2. I exist at the boundaries at both, so they both get a closed dot. Okay, so this one gets a closed dot, and 2 will also get a closed dot. Okay, so again, if I plug in 0 to my function, 0 would be the output, not 2. Open dot, close dot. And my next function in this piecewise function is 1/2 x minus 4. So it's a regular exponential 1/2 function, but shifted to the right by 4 units. So one thing I could do is just understand it's an exponential function. Plug in my boundary, right? What happens when I plug in 2 here? I got 2 minus 4, which is -2. So 1/2 to the -2 power is actually 4, right? You know, I can do this in my head. If you need to write this on paper, that's fine. So at 2, I have an output of 4 because this is the function, which means that I have a point in common here. Okay. So for my next function, it's going to start here, and I'm just going to keep cutting things in half. So I start at 4, and then the next one over, I'm half of that, so I'm at 2. And the next one over, I'm half of that, so I'm 1. The next one over, I'm half of that, so I'm 1/2. And then a quarter, and then an eighth, and so forth, because my rate of growth here is 1/2. So every time I have a previous value, I'm cutting it in half for the next value. Right. Okay. So 4, the next one I'm at 1/2, at the next one I'm 1, at the next one I'm 1/2, and then so forth. So it's a decreasing exponential function. It has one point in common, so I don't have to worry about open dot, close dot, because it exists. It's a shared point for both sides there, right? So this is the graph of my piecewise function. As you notice, it is what we call discontinuous, or a non-continuous function. In order to graph this, I have to lift my pen from the paper at this point and at this point, okay? So I'm a constant function here. I am a line over this interval of existence. I'm a quadratic on this interval of existence, and I'm an exponential function on this interval all the way to infinity. Okay. So a couple of things that we want to talk about, just to refer back to some of the ideas we're going to talk about quite a bit here, is this idea of increasing and decreasing, right? So my function is increasing from -4 to 0, right? Because I'm going up in value, and I'm also increasing from 0 to 2. I'm not increasing over the entire interval, however, because I have a point where I'm going from large values to smaller values. So I'm not going to say it is completely increasing. I will talk about it increasing from one interval and then the next interval of increase. Okay, so I join those with the union symbol. This is one interval of increase, and this is another interval of increase, but it is not from -4 to 2 because there are larger values here than there are here. So it's not increasing. The definition of increase is as I move forward, I keep getting larger or being the same value. Okay. This is not considered increasing either because I am always the same value. There should be some sort of levels of change as I move forward. So this is a constant. This is an interval of constant value, an interval of increase, a secondary interval of increase. So these two are joined with an OR symbol. Okay, I'm decreasing from 2 to infinity. Right? Notice I'm not including the endpoints here because at the endpoints I'm not increasing or decreasing. I have a fixed value. So the definition of increasing and decreasing means for the next value, for the next input value, I'm larger than or equal to the previous input value. And so here I'm at the end, there is no next value because at the next value I'm actually decreasing. So I don't include the endpoints when I talk about intervals of increase or decrease. Okay, it's always going to be an open bound for increase, decrease intervals. Another thing that we like to talk about, as we saw before, is when we're at a max or a minimum value. Okay, so we also not only talk about when we have a localized maximum or a localized minimum, but overall, what's the largest value period? Which is something that's very, very interesting to us as we go through this course. So for this function, my maximum value is 4. This is the largest output I have over the entirety of the function, over the whole life of my function. My absolute minimum value is 0. And I'm not using this because I'm not actually 0 at -4. I'm actually 2 at -4. So this doesn't count as my minimum. But this is where my absolute minimum is. Okay? So I have an absolute max of 4 and a minimum value of 0. Okay? And that's how we kind of analyze our functions.